Hi everyone, I'm Nahal Norouzi. I'm a PhD student at the University of Central Florida, and my talk today is about our project, which is about shared gaze environments in augmented reality. And unlike Yuan's project that he just talked about, by shared gaze here we mean sharing eye gaze. So just to clarify that there is a difference between our projects. So augmented reality has been extensively used as a collaborative platform to facilitate multiple users, both for co-located and remote collaboration. And these are just a number of examples, but there are a lot of work in this field out there. And with advances in AR technology, in recent years there has been plenty of applications developed to facilitate collaborative-based work, such as the example you can see on the top figure, which is, for instance, for police officers for crime scene investigation, or the example on the bottom, which is for medical training and surgery. In normal, natural face-to-face collaboration, an important aspect is that collaborators can actually see each other's facial expressions, they can see each other's gesture, and be aware of each other's focus of attention. And in AR, so this is an example for natural face-to-face interaction. In AR, as you can see, adding emphasis to some of these nonverbal cues can help the collaboration, and also it's important to be able to restore some of the cues, some of the nonverbal cues that is lost when we add AR to the mix. And because of the importance of these nonverbal cues during collaboration, many researchers have actually looked at a concept called awareness cues. So the question is, what are awareness cues? Awareness cues are additional or emphasized body gestures, head direction, gaze direction that is added to the view of the collaborators, regardless of the domain. So it can be HCI, it can be AR, it can be VR. And these are a few examples for AR and VR. So researchers have included these awareness cues to their setups for AR and VR. And the important question is, why are they doing that, and why are awareness cues so important? So the reason awareness cues are important, based on the findings of all these important work, is that awareness cues actually enhance the quality of communication between collaborators. And at the same time, they can increase performance of collaborators. So because in our project we are talking about sharing eye gaze information, there are a number of ways that you can visualize shared gaze. One of them is, for instance, a cursor. A very common way is to use gaze rays. It's a little difficult to see the gaze ray in this figure. So there's a gaze ray from the yellow guy and the blue guy. I can emphasize that here a little more. So gaze ray is basically a line rendered from the user's eye or the center of their eyes that showing their direction of their focus of attention. And in shared gaze AR environments, similar to many collaborative environments, we are dealing with issues with error. There are a lot of errors that we need to deal with. For instance, to have several devices that are going to be updated with each other, these devices need to be networked. And with networking, depending on the complexity of the setup, there are going to be certain errors such as latency and dropout that we have to deal with. And although shared gaze is very beneficial for collaboration and enhances the quality of communication, with current eye trackers we are also dealing with certain errors that are inherent to the eye trackers that we're using now. So to give you a few examples, for instance, in the bottom figure, the left figure, you can see that the eye tracker that's used in that example is very precise because it's consistently replicating the gaze points, but at the same time it's not very accurate because there's that angular offset from the actual target. And in the example on the bottom right, the system is both imprecise and inaccurate because the gaze points that are reproduced are very scattered, and all of them have some offset from the actual gaze target. We are all aware that errors exist, both in networking and eye tracking, but we felt it can be important and beneficial to understand in a structured way the impact of these errors. So with our project, we wanted to understand the impact of error level and error type on users' objective performance and also on their self-assessment of their performance and their subjective experience in general. To try to explore this area and to answer these questions, we actually created a shared gaze platform that facilitates two users, and both users in augmented reality, and both users are able to see each other's gaze points in AR. But for this experiment specifically, we kind of removed one of the real users and replaced them with a virtual partner, as you can see. And we had this setup that the virtual partner is actually a police officer that is going to identify a target amongst a crowd of people. And the virtual partner did not talk to the participants, so the only means of communication for the virtual partner was a gaze ray, as you can see, the white ray, starting from the virtual partner's eyes. And to make sure that this gaze ray is realistic and natural, we actually recorded real eye gaze recording and normalized them and then fed them to the system. And one more thing is that the gaze ray of the partner can actually follow the different targets in the crowd, which I'll talk about in the next slide. And also it can scan the different body parts on the targets randomly to kind of give the illusion that it's trying to scan for different targets. So to be able to actually understand what is the influence of error type and error level on performance, we designed this search task. We had 9 virtual humans with numbers floating over their head, and these virtual humans were able to pace back and forth in our lab space between predefined points, randomly assigned speeds, and also randomly assigned positions only along the z-axis. And one thing about the task was that our participants, who you can see in this figure, are standing 1 meter apart from the virtual partner. Those participants were given the task that they have to be able to identify for each trial, identify a target that the virtual human is actually following with their gaze, virtual partner. And they had 60 seconds to do so, and then when they figured out who the target is, they had to just shout out the number and say it's person 2 or person 3. And here actually you can see an example that the virtual partner is looking at person 8 and it's scanning person's 8 body randomly. And at some point when participants had identified who they think the target is, they would just tell us the number. So now I'm going to talk more about our experiment and our variables. Because we wanted to understand the influence of error and error type on participants' performance, we wanted to control everything as much as possible, we simulated the different error types. So the first error type that we simulated was errors in accuracy. So in the middle figure, as you can see, the left figure is where there is no error, and the right figure is where there is an angular offset from the target when the gaze points are reproduced. And to test different error levels, for our error levels, not just for accuracy, but for all the error types, we try to refer to past literature and the values that manufacturers report to choose those error ranges. So for accuracy, we chose 6 discrete levels between 0 to 5 degrees. Our next error type was errors in precision. As you can see here, the left figure is no error, and the right figure you can see that the eye tracker, which has errors, is not actually able to reproduce the same gaze points on the target consistently. For this error type, we tested the values of 0 to 2.5 degrees, so 6 discrete levels. Our next error type is latency. So for latency is basically depending on how many milliseconds the system has latency, so let's say 10 milliseconds, then the gaze points are always going to follow the previous positions of the target instead of the actual position of the target. And for this type of error, we tested the values of 0 milliseconds to 1,000 milliseconds. Our last error type was dropout, or dropped frames. As you can see here, for instance, the no error condition, 5 gaze points were supposed to be transferred to the user, but 3 of them were dropped and only 2 of them were transferred. So for this error type, we tested the values of 0% no dropped frames to 90%. Our last independent variable was target distance. So for our experiment, the targets, the virtual humans that were supposed to be targets were only positioned at 3 different distances, so either close, medium, or far. And they were randomly assigned to these positions to make sure that there is no learning effect for our participants. So to tell you guys about our conditions, I'm just going to briefly go over all of our independent variables. So we had 4 different error types. For each error type, we tested 6 discrete error levels. And again, for each error type, we tested 3 different target distances, which results in 72 trials total, or basically 4 condition blocks, each of them consisting of 18 trials. And for all of our participants, we randomized the 4 blocks and also randomized the 18 trials within them. And it was a within subject study. Okay, so for our measures, as I've been saying, we wanted to understand the influence of error on performance. So we had 2 ways to measure objective performance. One of them was response time. So we basically measured how fast within the 0 to 60 second time interval for each trial they can identify a target, and also whether or not their answer is correct. We also asked participants at the end of each condition block to assess their own performance, which was between 0% if they thought they did horribly to 100% if they thought they got all the answers right. To give a brief overview of our participants, we had 21 participants total, 7 females, 14 males, and the average age was 23 years old, and all of them were affiliated with our university. Okay, so I'm going to talk about some of our findings of this study. Just to give you a brief overview of the plots before I get started. So the horizontal axis for all of the plots is basically the error level. So for accuracy here, it's 0 to 5 degrees, 6 discrete error levels. And for the vertical axis, it's the top figure, it's response time, so it's 0 to 60 seconds because each trial was 0 to 60 seconds. And for the bottom figure, it's error rate, so it's 0% to 100% basically. And for looking at errors in accuracy, we noticed interestingly that as we increased the error level, participants' response time and error rate started increasing. And at some point around 3 degrees, we actually started seeing objective drop in performance. For errors in precision, we didn't really see any objective drop in performance. As you can see, as the error levels increased, participant performance maintained basically the way they started. So similar to accuracy, with latency, we also observed that as we are increasing the error levels, participants' performance is getting worse. So response time is increasing and error rate is also increasing. And we started seeing trends of drop in performance around 400 milliseconds and a significant drop around 600 milliseconds. With dropout, very similar to precision, we did not really see a significant drop in performance. The only time we saw that significance was with 90% dropout error, which is a large amount of error, actually. For subjective results, to give you a brief background about this, there are some previous work that look at how participants assess their own performance. And it's not just in collaborative setups that there are different people, but in general AR/VR setups that the user is getting some feedback from the system. And interestingly, in those setups, they notice that even if they inject error to the system, and they don't tell the participants attribute that error to their own lack of performance instead of thinking that there might be something wrong with the system. And we wanted to see if we see a similar trend with our results. And interestingly, although we were introducing a lot of error, we actually noticed that for most of our error types, so accuracy, precision, and dropout, we saw a similar trend that participants attributed their uncertainty to themselves instead of thinking that the system has a lot of errors. To talk about basically the take-home message is that we realize that errors in accuracy and latency can negatively influence participants' performance more compared to precision and dropout. So it's important to pay attention to those errors more when we are building our systems. Also, when we were qualitatively talking to our participants, we noticed that since in our task the targets were dynamic, so they were moving back and forth with different speeds, we noticed that participants very much relied on trying to match the gaze speed and the target speed when the error levels were high. And also, they looked at the direction changes of a target to try to identify who the target can be. Another interesting thing was that, similar to past research, we also noticed that participants perceived their performance to be much worse, even though they actually performed very well. To just provide a brief guideline, we noticed that for error level, for accuracy, at an acceptable, relatively acceptable amount of error, the participant can maintain their performance is around 2 to 3 degrees. And for latency, it's somewhat around 400 milliseconds to 600 milliseconds. And to give you a brief a relative understanding of what that means, for all of those errors that I just talked about, it will be something like almost 37 centimeters offset from the actual target. And that's why errors in accuracy and latency cause so much trouble for our participants, because there is a higher chance for them to make a mistake, either make a mistake or need more time to try to identify the target correctly. To conclude, we created a shared gaze platform in augmented reality. We simulated 4 types of errors and introduced them to our system and tried to understand the influence of these errors in our setup and participants' performance and experience. And we are providing some guidelines for tasks such as gazing at human-sized objects, errors that can be acceptable for participants to maintain in their performance. For accuracy are around 2 to 3 degrees, and for latency are around 400 to 600 milliseconds. For our future work, we think it can be interesting to also look at static search tasks and the influence of error on static search tasks, because they don't have those additional cues that dynamic search tasks have, such as speed, movement pattern. We also think that looking at different gaze visualizations and how they influence error and how they communicate information can also be very important, specifically if the context of the task is changing. And also we think that researching more and exploring the whole target distance area can be very important, because in our results we found some significance for target distance, but it wasn't very clear, because sometimes the closer target distances were significant, and we think that was probably because of the limited field of view in HoloLens. So we think that area and also longer target distances should also be researched. Thank you so much for your attention. That is true, but for instance, People Labs is an eye tracker that we actually use for the platform that we had for 2 real users actually. And People Labs reports its 3D, which is the type of tracking which is useful in AR. They report their 3D accuracy to be around 2.5 and 3 degrees. And that is when there is perfect calibration and not a lot of movement. So depending on the context of the study, we think that a lot can happen for the accuracy to drop significantly. That's why we wanted to kind of cover the area that they report and also go a little higher to see what happens if you go, for instance, 1 degree or 2 degree higher.
So eye trackers are all visual, right? So they use actual 3D pointing.
Yeah.
And you were visualizing that, right?
We were not giving the actual 3D points, so our gaze ray was actually going towards infinity. So for this project, we were assuming that we don't have depth information, basically. Yeah.
So if you would assume that you cannot increase the eye tracking accuracy for whatever reason,
yeah.
the talk of the past will most likely rate the eye tracker every 5 minutes. how would you go on about still supporting these therapies and improving this performance? You talked about visualization techniques in your future work. Can you give us a little bit of insights, speculations on how you would address this problem?
Yes, actually, that's very interesting. One thing is that with our results, although the error levels were kind of high, the participant performance were actually quite good, even with, for instance, 5 degrees offset in accuracy. So that's kind of promising. And we think for our specific task, that's somewhat related to the fact that there were other cues, so speed or direction. But one thing that I think it can be helpful to kind of resolve that if there are none of those additional cues is maybe with gaze visualization. So adding, like instead of just using a thin line, maybe increasing it so it's like a frustum, or adding like a pointer at the end to kind of bold the end of the gaze point. So these are things with visualization that may be able to kind of improve this issue with accuracy or precision. Yeah.
Questions? I have one last.
Of course.
So, those virtual characters, I think they were randomly walking back and forth, and so also the inter-target distance, I think, changed from time to time, right? So the distances of occlusion changed, you showed it in the video. Did you notice that the participants actually identified a specific target and specific spatial configurations? For example, when the actual target was not occluded, or it was distant to other targets, was above a certain threshold. Did you investigate this issue?
This is something that we have collected data for. Okay. So we have data, it's not analyzed yet, but we do have data about, for instance, the speed of all the targets for each trial. So we will be able to analyze, for instance, if they had an incorrect answer, what was the speed of their incorrect answer, and where was that incorrect target placed relative to the actual correct target? So we can analyze that part and understand. Does that answer your question?
Okay. Any more questions? Well, then, thank you again.
Thank you.